The universe whispers its secrets in a language of patterns. Across every scale, from the quantum foam to the cosmic web, a hidden order seems to guide reality itself. We are about to embark on a journey through 30 of the most mind-bending theories that attempt to decode this cosmic cipher. You will discover how the fabric of space-time might be an illusion, and whether our entire existence could be a sophisticated simulation. What if the Big Bang was not the beginning, and what mysterious force is pulling entire galaxies off course? By the end, you will see the cosmos in a completely new light. Which hidden pattern do you think holds the key to reality itself? A spiral galaxy rotates in the void, its arms sweeping out in an elegant curve that seems almost familiar. This cosmic shape is mirrored in the swirl of a hurricane seen from space, and even in the arrangement of seeds on a sunflower. The thread connecting them is a simple sequence of numbers discovered by an Italian mathematician centuries ago. 1, 1, 2, 3, 5, 8, 13. Each new number is the sum of the two before it. This is the Fibonacci sequence, and its appearance throughout nature is so frequent it cannot be easily dismissed. This sequence gives rise to a special number known as the golden ratio, approximately 1.618. When used to divide a line, the ratio of the whole to the larger part is the same as the larger part to the smaller. This proportion is found in the spiral of a nautilus shell, the branching of trees, and the proportions of our own bodies. Is this widespread presence just a happy accident of physics and biology, or is it a signature, a subtle clue that the universe has a preferred language of form and growth? The patterns suggest a fundamental rule, a hidden algorithm that space-time itself might be following, from the smallest bud to the largest galaxy. What kind of universe would choose to express itself through mathematics so consistently? This mathematical perfection hints at a universe built from code, but what if even the dimensions we perceive are an illusion? The holographic principle proposes a reality so strange it challenges our most basic assumptions. It suggests that our rich, three-dimensional world, with its depth and volume, might be a projection from a flat, two-dimensional surface at the very edge of the cosmos. Think of the hologram on a credit card. That shimmering, three-dimensional image is not truly deep. It is encoded on a flat plastic film. In a similar way, our universe might be a cosmic hologram, with all the information that describes every star, every planet, and every one of us stored on a distant two-dimensional boundary. This is not just a philosophical idea. It emerged from a deep conflict in physics, the black hole information paradox. When something falls into a black hole, according to our current understanding, it is lost forever. Its information, the unique arrangement of particles that made it what it was, seems to vanish. This violates a fundamental law of quantum mechanics, which states that information can never be truly destroyed. The holographic principle offers an elegant solution. It suggests the information of whatever falls in is not lost inside the black hole, but is instead perfectly preserved, encoded on its two-dimensional event horizon, the surface from which not even light can escape. Our reality, then, might be a vast and complex translation. The solidity of a table, the warmth of sunlight, the vast emptiness of space, all could be a magnificent projection from a simpler, flatter realm of information. If this is true, then the universe is not just whispering in a language of mathematics. It is performing a breathtaking magic trick, convincing us of a depth that is not fundamentally there. This idea of a projected reality forces us to question the very nature of our cosmic origins. What event could have set the stage for such a bizarre and magnificent illusion? The leading theory points to a moment of unimaginable fury in the first sliver of a second after the Big Bang, a period known as cosmic inflation. For a fleeting fraction of a moment, the universe did not just expand, it exploded into being, inflating from a subatomic speck to a vast cosmic landscape faster than the speed of light. This violent stretching smoothed out the infant cosmos, explaining why the universe appears so uniform in every direction we look. The most compelling evidence for this incredible growth spurt is etched into the oldest light we can see, the cosmic microwave background. This faint afterglow of the Big Bang is not perfectly smooth. It contains tiny, frozen ripples of temperature, the seeds that would one day grow into all the galaxies and cosmic voids we see today. These ripples match the predictions of inflation perfectly, a cosmic fingerprint from the dawn of time, but the theory's implications are even more staggering. Most models suggest that this inflationary process never truly stopped. Instead, it may have ended only in our local patch of reality, while continuing eternally elsewhere. This leads to the breathtaking concept of the multiverse. Picture a boundless, bubbling cauldron of space-time, where new bubble universes are constantly budding off from the inflating background, each one a self-contained cosmos with its own unique set of physical laws. In one bubble, gravity might be repulsive, preventing stars from ever forming. In another, the fundamental constants could be slightly different, making chemistry and life as we know it impossible. Our universe is not special or central. It is simply one bubble among an infinite froth, a single planet in a cosmic archipelago where the laws of physics are as variable as the weather. This raises a profound philosophical question. Are we just incredibly lucky to have won the cosmic lottery, finding ourselves in a rare bubble where the conditions are just right for our existence? Or does an infinite multiverse make our presence somehow inevitable? The search for hidden patterns has led us to a cosmos of potentially infinite variety, where our own reality is just one possible verse in an endless cosmic poem. This staggering idea of a multiverse offers a potential answer to one of the most profound puzzles in all of science. Why do the fundamental constants of our universe seem so perfectly tuned for our existence? The force of gravity, the strength of the nuclear forces, the mass of an electron. If any of these values were altered by even a tiny fraction, the cosmos as we know it would not exist. Stars would never have ignited, complex atoms would never have formed, and life would have been an impossibility. This observation is the heart of the anthropic principle. In its weak form, the principle is almost a truism. It simply states that we, as observers, must find ourselves in a universe capable of supporting life, because in a universe that could not, we would not be here to ask the question. It is a statement about our own inevitable location within the vast landscape of possibility. The strong anthropic principle, however, ventures into far more controversial territory. It proposes that the universe must have properties that allow life to develop within it at some stage in its history. This version edges toward the idea of a universe with a built-in purpose, one that is in some sense designed or constrained to eventually give rise to conscious observers. So which is it? Are we the product of an astonishingly lucky cosmic accident, a random roll of the dice in a single universe where every constant just happened to fall into the narrowest of viable ranges? Or does the multiverse provide a more natural explanation? In an infinite froth of bubble universes, every possible combination of physical laws and constants will be realized somewhere. In the vast majority of these universes, the conditions will be sterile and lifeless, but in a tiny, statistically inevitable fraction, the numbers will line up just right. We should not be surprised to find ourselves in one of these rare, habitable bubbles because we could not exist anywhere else. The very fact of our existence selects for the kind of universe we observe. The anthropic principle, whether weak or strong, forces us to confront the role of the observer in the cosmos. It suggests that our presence is not a separate phenomenon from the laws of physics, but is inextricably linked to them. We are not just living in the universe in its specific form seems to require our gaze to give it meaning. But what if this cosmic fine-tuning points to something even stranger, a connection between consciousness and the very fabric of reality? This notion that our reality is a finely tuned stage for consciousness leads to one of the most unsettling possibilities of all. What if the stage is not just tuned but entirely constructed? The simulation hypothesis proposes that our universe, with all its galaxies, history, and personal experiences, is not base reality, but an artificial construct, a simulation running on some advanced civilization's computer. The argument, formalized by philosopher Nick Bostrom, presents a stark trilemma, three possibilities, one of which he argues must be true. First, almost all civilizations at our level of technological development go extinct before they can create realistic simulations. Second, any civilization that reaches such a technological maturity has no interest in running simulations of its own past. Or third, we are almost certainly living in a simulation. The logic is as simple as it is profound. If even a tiny fraction of advanced civilizations run a large number of high-fidelity simulations, then the number of simulated minds would vastly outnumber the minds in the original base reality. Therefore, if such simulations are possible, any randomly selected conscious being, like any one of us, is statistically far more likely to be one of the simulated beings. It is a numbers game, and the odds are not in favor of our reality being the prime one. But is this more than just a philosophical puzzle? Some scientists speculate that if our universe is a simulation, there might be detectable glitches in the matrix, tiny errors or shortcuts in the code. Just as a video game might simplify physics in the distance to save processing power, our universe might show signs of a finite resolution at the smallest scales. Physicists have even looked for such artifacts in the cosmic microwave background or in the behavior of high-energy particles, searching for a pixelation of space-time itself. The counterarguments, however, are just as compelling. The computational power required to simulate every particle in a universe is staggering, perhaps physically impossible even for a super-advanced civilization. And if the simulation is so perfect that it is indistinguishable from reality, does the distinction even matter? Our joys, our struggles, the beauty of a sunset, all of it feels profoundly real to us. Yet the hypothesis remains a powerful and haunting modern myth, a reflection of our own technological trajectory. As we ourselves begin to create immersive virtual worlds, we are forced to wonder if someone or something has already walked this path before us. This idea of a simulated reality built from lines of code presents one vision of a patterned cosmos. Yet another pattern emerges not from silicon, but from the raw geometry of nature itself, repeating its beautiful, broken symmetry at every conceivable scale. The universe appears to be fractal. A fractal is a shape whose intricate details repeat themselves as you zoom in, a never-ending cascade of self-similarity. The branching of a tree, from its thick trunk to the smallest twig, mirrors the branching of our own lungs and blood vessels. A bolt of lightning carves a jagged path through the sky that looks remarkably similar to the dendritic patterns of a river delta seen from space. These are not mere coincidences. They are the visible signature of a universe built upon efficient, recursive processes. The mathematician Benoit Mandelbrot gave this hidden geometry a name, fractals, and revealed their stunning complexity through his now famous Mandelbrot set. A single, simple mathematical rule, when iterated over and over, generates an infinitely complex border, a coastline of endless detail where the same swirling patterns appear no matter how deep you dive into the calculation. This raises a profound question about the cosmos itself. Is the universe in its grand architecture truly fractal? When we map the distribution of galaxies, we do not see a random scattering. Instead, we find a cosmic web, a vast, interconnected lattice of galaxy clusters and superclusters separated by enormous, empty voids. This web is not smooth. It is clumpy and filamentary, and when you look at a small section of it, its structure bears a striking resemblance to the entire larger network. From millions of light years across to hundreds of millions, the pattern of clustered matter and empty space seems to hold a suggestion of a self-similar universe. But does this fractal pattern continue all the way up to the very largest scales of the cosmos? The current scientific consensus suggests that it does not. Observations of the cosmic microwave background, the ancient light from the Big Bang, indicate that on the very largest scales, beyond about 300 million light years, the universe transitions to a state of smooth homogeneity. The clumps and voids average out and matter becomes evenly distributed. It seems the fractal universe has a maximum zoom level. This breakdown of self-similarity is not a failure of the pattern, but perhaps its most important clue. It tells us that the processes that shaped our cosmos, the relentless pull of gravity and the initial conditions of the Big Bang, have a fundamental limit to their recursive influence. The universe is fractal-like, but not perfectly so, a broken symmetry that reveals the specific history and fundamental laws that gave it form. So we are left with a cosmos that is almost fractal, a place of deep, repeating patterns that ultimately give way to a smoother, more uniform whole. This interplay between the endlessly complex and the ultimately simple may be the most profound pattern of all. The same mathematical harmony that builds fractal coastlines might also compose a silent symphony for the stars. Long before telescopes revealed the structure of our solar system, the philosopher Pythagoras proposed that the planets moved in perfect celestial spheres, each emitting a hum based on its orbital speed. He called this the music of the spheres, a literal cosmic symphony inaudible to human ears. Centuries later, the astronomer Johannes Kepler was so captivated by this idea that he devoted years of his life to finding the musical intervals between the planets' orbits, convinced that God had created a universe based on geometric and harmonic perfection. While their literal vision of a singing cosmos faded, the underlying principle of resonance did not. We now see its echoes everywhere in our solar system. Orbital resonance occurs when two orbiting bodies exert a regular, periodic gravitational influence on each other, often synchronizing their orbits in a simple ratio. Look at Neptune and Pluto. For every 2 orbits Neptune makes around the Sun, Pluto makes 3. This gravitational dance keeps their paths stable, preventing them from ever colliding. Jupiter's moons are another example, with Ganymede, Europa, and Io locked in a precise 1-2-4 resonance. This is not just orbital mechanics, it is the solar system finding its natural, harmonious rhythms, a direct descendant of the music Pythagoras imagined. But the resonance extends far deeper than planetary orbits. The universe itself may have a fundamental frequency. When scientists examined the cosmic microwave background, the afterglow of the Big Bang, they found faint, resonant waves like the lingering echo of the universe's first and loudest note. Some theories even suggest that the fundamental strings in string theory vibrate at specific resonant frequencies, and that every particle we see is essentially a different note played on this tiny cosmic instrument. So perhaps the ancient philosophers were not entirely wrong. They simply lacked the instruments to hear the true score. The music of the spheres is not a literal melody, but a profound mathematical harmony written into the very laws of physics, from the graceful dance of planets to the quantum hum of reality's smallest building blocks. This cosmic harmony, however, shatters into pure mystery when we descend to the quantum realm. Here, a single event can create a pair of particles that remain mysteriously linked for life, no matter how far apart they travel. This is quantum entanglement, a phenomenon so strange that Albert Einstein himself famously dismissed it as spooky action at a distance. Imagine creating 2 coins that are forever linked. You send one to a friend on the other side of the galaxy. The moment you flip your coin and see it land on heads, you know with absolute certainty that your friend's coin has simultaneously landed on tails. This is the essence of entanglement. The particles, like these coins, have no definite state until one is measured. The act of measurement instantly forces its partner into the corresponding state, a connection that seems to transmit information faster than the speed of light. This non-locality, this ability to influence something instantaneously across a vast distance, violates everything we know from our classical, everyday world. It suggests that at the most fundamental level, the universe is not a collection of separate, independent objects. Instead, it points to a deep and hidden connectedness, a cosmic web of relationships where space itself might be an emergent property, not the fundamental stage we perceive. This interconnectedness could be one of the universe's most basic patterns, a thread woven into the fabric of reality that ties everything together in a way we are only beginning to comprehend. If entanglement is a fundamental feature of the cosmos, then what appears as empty space to our eyes might be teeming with an invisible lattice of instantaneous connection, a silent, spooky network that underpins all of existence. This invisible quantum connection suggests a cosmos that is fundamentally unified, yet it leads to a paradox that threatens to unravel our entire understanding of reality. The Boltzmann brain thought experiment begins with a simple, undeniable fact. The universe is overwhelmingly chaotic, a vast sea of random particles and energy. But against all odds, we find ourselves in a pocket of exquisite order, a universe with galaxies, planets, and conscious minds. The second law of thermodynamics states that disorder or entropy always increases. So how did we get here? The physicist Ludwig Boltzmann proposed a potential answer. In a vast and eternal sea of chaos, random fluctuations will occur. Most are small and insignificant, but given enough time, even the most unlikely event will happen. A random jiggle of atoms could, by sheer accident, momentarily assemble a fully formed, self-aware brain, complete with false memories of a past that never existed and a sensory experience of a universe that is not really there. According to the mathematics of probability, in an infinite and chaotic cosmos, it is astronomically more likely for a single, disembodied brain to pop into existence through a random fluctuation than for an entire, ordered universe spanning billions of light years to form. The odds overwhelmingly favor you being a Boltzmann brain, a fleeting consciousness that just randomly formed in the void, complete with the illusion of reading this script, rather than a person with a real history in a real cosmos. This is not just a strange idea, it is a direct challenge to our most basic assumptions. If our best cosmological models point to a reality where we are more likely to be fleeting illusions than enduring beings, then something in our models is profoundly wrong. The paradox forces physicists to reconsider the very nature of time, eternity, and the initial conditions of the Big Bang. Perhaps our universe is not a random fluctuation in an eternal void, but the product of a very specific, low-entropy beginning that makes coherent, long-lasting structures like galaxies and people the norm, not the miraculous exception. The Boltzmann brain reminds us that the universe's greatest hidden pattern might not be in the stars, but in the fragile, ordered nature of our own consciousness and the mysterious laws that allow it to exist at all. The unsettling thought of being a fleeting illusion in a chaotic void forces us to question the very singularity from which our cosmos was born. But what if the Big Bang was not a true beginning at all, but merely a violent transition in an endless, repeating cycle? The ekpyrotic universe model offers this radical alternative, replacing the moment of creation with a cosmic collision. In this theory, our entire three-dimensional universe exists on a membrane or brain, a vast sheet-like object floating within a higher dimensional expanse called the bulk. Picture our reality as a single, impossibly large slice of bread adrift in a multidimensional loaf. The Big Bang, in this view, was the moment our brain collided with another parallel brain. This titanic impact did not create matter and energy from nothing, but instead injected an immense amount of energy into our brain, heating it to an incredible temperature and initiating the expansion we now call the Big Bang. This solves one of the great puzzles of the Standard Model. Why is the universe so remarkably uniform? Because the colliding brains were flat, parallel sheets, the energy of their impact was distributed evenly across the entire surface of our brain, resulting in the smooth, uniform cosmos we observe today. After the collision, the brains bounce apart, and the universe on our brain expands and cools, allowing for the formation of galaxies, stars, and planets. But the story does not end there. The gravitational attraction between the brains eventually draws them back together, leading to another collision, another Big Bang, and the birth of a new cosmic cycle. This process repeats eternally, with no beginning and no end. The entire history of our universe, from its fiery start to its eventual cold demise, is just one phase in an infinite cosmic rhythm. This cyclic model makes a dramatic prediction that could one day be tested. The collision of such immense structures would have sent powerful gravitational waves, ripples in the fabric of space-time, echoing through the newborn universe. While the primordial gravitational waves from the initial moments of the Standard Big Bang would have a specific signature, the waves from a brain collision would be different. Future observatories like the Laser Interferometer Space Antenna, or LISA, may be sensitive enough to detect the faint imprint of these waves, listening for the echo of that long-ago collision. If they find it, our entire understanding of cosmic origins would be rewritten. We would not be the product of a single, unique creation event, but the inhabitants of one cycle in a universe without end, a cosmos forever being reborn from its own ashes. Yet even the echoes of a cosmic collision might carry a strange and unexpected signature. As we map the faint glow of the cosmic microwave background with ever greater precision, a peculiar anomaly emerges, one so unsettling that cosmologists have nicknamed it the axis of evil. This is not a malevolent force, but a mysterious alignment in the oldest light in the universe. The cosmic microwave background should be a nearly uniform tapestry, a remnant of the early universe's hot, dense state. According to the cosmological principle, a core tenet of modern science, the universe should look roughly the same in every direction, with no preferred center or axis. But the data reveals something different. Certain large-scale features in this cosmic afterglow, the hot and cold spots that represent the seeds of future galaxies, appear to be subtly aligned along a particular plane, a single axis that runs through the cosmos. It is as if the universe has a quiet, hidden spine. The immediate question is whether we are seeing a ghost in the machine. Could this alignment be a mere statistical fluke, a chance pattern that appears significant only because we have not collected enough data? Or is it an artifact of our own measurement, perhaps a contamination from the glow of our own Milky Way galaxy that has not been perfectly subtracted from the maps? Scientists have rigorously tested these possibilities, and the anomaly stubbornly persists. If it is real, the implications are profound. It could mean that the cosmological principle is wrong, and the universe is not isotropic after all. It might possess a fundamental lopsidedness, a preferred direction imprinted upon it at the moment of its birth. This opens the door to even more exotic explanations. Perhaps the axis of evil is a cosmic fossil, a scar left by the violent physics of the pre-Big Bang universe. In cyclic models like the ekpyrotic scenario, the collision of brains might not have been perfectly symmetric, potentially leaving a directional imprint on the newborn cosmos. Alternatively, this alignment could point to the influence of something entirely outside our observable universe, a structure so vast that its gravitational pull tugs on the fabric of our entire cosmic horizon. Is the axis of evil a statistical mirage, or is it the first faint clue that our universe is embedded within a far grander and far stranger reality than we ever imagined? This mysterious cosmic axis hints at a universe that is not perfectly uniform, a lopsidedness that might be driven by something immense lurking just beyond our sight. For decades, astronomers have known that our Milky Way, along with thousands of other galaxies, is being pulled in a specific direction by a colossal gravitational force. This region of space, located about 250 million light-years away in the direction of the Centaurus constellation, is known as the Great Attractor. It exerts a pull so powerful that it dominates the motion of an entire supercluster of galaxies. For a long time, its true nature was hidden from our view, shrouded by the dense band of stars and dust in our own galaxy's plane, a zone of avoidance that blocked our optical telescopes. But we have since peered through the cosmic dust with X-ray and radio eyes, revealing that the Great Attractor is not a single, monstrous object, but a massive concentration of matter, a gravitational focal point where countless galaxies are swarming together. It is the center of our local gravitational universe, the heart of the Laniakea supercluster, a vast cosmic continent to which our Milky Way is just a distant suburb. The puzzle deepens when we look beyond this local pull. Astronomers studying the motion of distant galaxy clusters found something that defies all conventional explanation, a phenomenon they call dark flow. Like leaves caught in a river current, these clusters are moving with a surprising, coherent velocity, all streaming in the same direction. This is not the predictable expansion of the universe, but an additional, peculiar motion. The most startling part is that this flow appears to be caused by something entirely outside our observable universe. The gravitational pull of the Great Attractor and all other known structures cannot account for it. It is as if our entire cosmic horizon is being gently tugged by a structure of unimaginable scale that lies beyond the cosmic microwave background, beyond the veil of our visible reality. What could possibly be massive enough to exert such an influence? One radical theory suggests that the dark flow is the gravitational fingerprint of another universe, a separate bubble in the multiverse cosmically close to our own. Just as the moon's gravity pulls on Earth's oceans, the mass of a neighboring universe could be gently pulling on the fabric of our own, creating this coherent drift of galaxies. Another possibility is that the universe is far more textured and irregular on the largest scales than we ever thought, with colossal, unseen mass concentrations warping space-time itself on a grand stage we cannot yet see. The Great Attractor and the dark flow together paint a picture of a cosmos that is not an island, but part of a much larger and deeply mysterious architectural whole. This endless cosmic drift hints at a reality without boundaries, but what if time itself is a circle? Roger Penrose's conformal cyclic cosmology proposes exactly that, a universe without beginning or end, eternally cycling through infinite rebirth. In this mind-bending vision, the cosmos is not a single story with a start and a finish, but an endless series of chapters which Penrose calls eons. Each eon begins with its own hot, dense Big Bang and expands for trillions of years until all matter eventually decays and black holes evaporate. The universe becomes a cold, empty sea of massless particles and radiation, stretching into an unimaginably vast and featureless void. Here, Penrose makes his most brilliant conceptual leap. In this state of ultimate expansion and decay, the very concept of scale loses all meaning. A universe devoid of particles with mass has no ruler, no way to measure distance. In this strange, conformal geometry, an infinitely large, empty universe becomes mathematically identical to an infinitely small, hot, dense one. The distant future of one eon seamlessly transforms into the Big Bang of the next. There is no singularity, no moment of creation from nothing, just an eternal, smooth transition from one cosmic cycle to another. To support this radical idea, Penrose and his colleagues have searched for fossils from a previous eon, and they believe they have found them. These are Hawking points, mysterious, circular spots in the cosmic microwave background that are significantly warmer than their surroundings. According to the theory, these are the final, explosive signatures of supermassive black holes from the previous eon. In the final moments of that ancient universe, as those black holes evaporated via Hawking radiation, they would have released immense bursts of energy. That energy, stretched across the conformal boundary into our own eon, would now appear as faint, circular imprints on the oldest light we can see. Not all cosmologists are convinced, arguing these points could be statistical anomalies or artifacts of the data processing. Yet the possibility remains electrifying. If true, it means our entire cosmic history, from the first second to the last star, is just one iteration in an infinite loop. The universe forgets itself, only to be born again from its own ashes, an eternal phoenix in the dark. This eternal cycle of cosmic rebirth rests upon a principle we take for granted: that information, the distinct identity of every particle and force, is never destroyed. Yet this foundational law of physics meets its ultimate challenge in the darkest corners of the universe. The black hole information paradox pits our two most successful theories against each other in a battle for the soul of reality. According to Einstein's general relativity, a black hole is defined purely by its mass, spin, and charge. If you were to throw a grand piano, a library of encyclopedias, or a single, unique snowflake into a black hole, the theory insists the black hole would not change in any way that reflects what fell in. All that intricate information about the piano's shape, the words in the books, the crystal structure of the snowflake, seems to be permanently erased from our universe when the black hole eventually evaporates through Hawking radiation. This violates a sacred rule of quantum mechanics, which states that information must be preserved. It can be scrambled, transformed, or hidden, but it can never be truly lost. The universe, according to quantum law, must always remember. So where does the information go? One radical proposal is the black hole firewall. Imagine the event horizon, the point of no return, not as an empty boundary, but as a searing wall of unimaginably high energy particles. The moment you cross, you and all your information are instantly incinerated. This firewall would prevent information from ever falling into the black hole in the first place, preserving the quantum rule but shattering our understanding of Einstein's smooth spacetime. Another, more subtle solution is black hole complementarity. This idea suggests that from the perspective of an outside observer, the information never actually crosses the event horizon. Instead, it is smeared and encoded onto the surface of the black hole, much like the holographic principle suggests. But from the perspective of the person falling in, they pass smoothly through the horizon, none the wiser. Both perspectives are correct within their own frames of reference, and the paradox only arises if you falsely try to combine these two incompatible viewpoints. The information is not in two places at once. It is described in two different, complementary languages. The most compelling modern answer brings us back to the holographic universe. If our reality is a projection from a two-dimensional surface, then a black hole is not a cosmic shredder. It is a cosmic hard drive. The information of everything that falls in is not lost inside the three-dimensional volume, but is perfectly preserved, pixelated onto the event horizon's two-dimensional surface. When the black hole radiates and shrinks, that information is slowly and carefully released back into the universe, albeit in a wildly scrambled form. The information was never truly gone. It was just stored in a language we are only beginning to learn how to read. This suggests that the universe is not just mathematically precise, but profoundly archival, ensuring that not a single bit of its cosmic story is ever forgotten. For centuries, one idea has anchored our view of the cosmos. The Copernican principle insists that our location in the universe is utterly ordinary, that we occupy no special place, no central throne. This principle of mediocrity is the bedrock of modern cosmology. But what if this foundational assumption is wrong? What if we are, in fact, living in a very special place after all, a cosmic backwater of staggering proportions? This is the unsettling premise of the giant void theory. Imagine our galaxy is not in a typical region of space, but at the center of a vast, nearly empty bubble, a cosmic void billions of light years across. In this scenario, the space around us would have a much lower density of matter than the universe at large. This emptiness would have a profound effect on our observations, particularly on the light from distant supernovae. When astronomers in the late 1990s measured these stellar explosions, they made a shocking discovery. The universe's expansion is not slowing down as expected, it is speeding up. The explanation that won the Nobel Prize was dark energy, a mysterious repulsive force woven into the fabric of space itself. But the void theory offers a radical alternative. There is no dark energy. The apparent acceleration is a grand illusion. Here is how the cosmic magic trick works. Gravity's pull is weaker in our local void because there is less matter to generate it. The space inside our bubble expands faster than the denser regions outside. When we look at a supernova in a distant, denser part of the universe, its light has traveled through both the faster expanding void and the slower expanding outer regions. This journey can trick us into thinking the expansion rate is increasing, when in reality, we are simply seeing the contrast between our underdense home and the average density of the cosmos. We are not measuring an accelerating universe, but our own atypical address. The implications are staggering. It would mean that the Copernican principle, the very heart of cosmological science, is flawed. Our place would be special, a rare and quiet oasis in a much more crowded cosmic landscape. This idea faces immense challenges, of course. For the illusion to work, the void would have to be unimaginably large, and we would have to be almost perfectly at its center. The odds of that seem vanishingly small, arguably just as puzzling as the dark energy it seeks to replace. Yet it forces a profound philosophical question. Have we, in our quest to avoid cosmic arrogance, embraced an even stranger truth, or have we simply failed to recognize our own exceptional location in the grand scheme of things? This very act of looking, of measurement, might do more than just reveal reality. It could be actively creating it. The quantum Zeno effect presents us with one of the most direct and bizarre demonstrations of this principle. In the quantum realm, an unstable particle, like a radioactive atom, has a certain probability of decaying at any given moment. But if you observe that atom continuously, if you repeatedly and rapidly ask the question, "Are you still there?" something remarkable happens. The probability of its decay drops to nearly zero. Your constant observation, in a sense, freezes the atom in its initial state. It is named after the ancient Greek philosopher Zeno, who proposed a paradox where a flying arrow must be motionless at every single instant of its flight. The quantum version suggests that by obsessively checking on the arrow, we can prevent it from ever moving at all. This is not just a theoretical curiosity. It has been demonstrated in laboratories where constantly measuring the state of a group of atoms prevents them from evolving, effectively trapping them in a single quantum configuration. The unsettling implication is that the passive, objective universe of classical physics simply does not exist at this fundamental level. Reality seems to require an interaction, a measurement, to transition from a haze of potentialities into a definite state. So where does that leave us, the observers? Does this mean a conscious mind is necessary to continuously observe the subatomic underpinnings of the world, literally holding the fabric of reality together by repeatedly looking at it? This is a profound and controversial leap. The more mainstream interpretation is that a measurement is just a physical interaction, a collision with another particle that forces a definite outcome, with or without a conscious being present. But the line between a simple interaction and a conscious measurement is blurry. If the universe only becomes concrete through a chain of such interactions, then the entire cosmos could be seen as a self-observing system, a vast network of measurements locking each other into place. The hidden pattern here might not be a geometric shape or a mathematical constant, but a dynamic process. The universe may not be a static, pre-recorded film, but a live performance that only manifests its scenes under the relentless gaze of its own participants. Are we merely witnessing the show, or are we, through the simple act of perception, an essential part of the cast, performing the continuous miracle of bringing solidity out of potential? If our observations are shaping reality, what then are the unseen architects shaping the cosmos itself? For decades, one of the greatest mysteries has been dark matter, the invisible substance whose gravitational pull holds galaxies together. We cannot see it, but we can see its handiwork in the way stars whip around galactic centers far too quickly for the visible matter alone to hold them in place. The leading candidate has been a hypothetical exotic particle, but another, far more dramatic possibility is emerging from the cosmic shadows. The primordial black hole theory suggests that dark matter is not made of particles at all, but of black holes, ancient relics forged in the furnace of the Big Bang's first second. In that initial, chaotic moment, pockets of space could have been crushed into ultra-dense knots by the extreme pressures, collapsing directly into black holes without the need for a dying star. These would not be the stellar mass black holes we know today, but a spectrum of sizes from as small as an asteroid to many times the mass of our Sun, all born in the universe's violent infancy. This idea was once on the fringes, but it has gained remarkable traction from a modern discovery, the detection of gravitational waves. When the LIGO Observatory first felt the ripple in space-time from two colliding black holes, astronomers were surprised by their mass. Each was around 30 times the mass of the Sun, heavier than what typical stellar evolution models predicted. One compelling explanation is that these were not the remains of dead stars but primordial black holes, meeting in a dark, cosmic dance that lasted billions of years. If such black holes are abundant, drifting through the galaxy in their countless trillions, they would exert a powerful gravitational pull on everything around them, yet emit no light. They would be, in effect, the perfect candidate for dark matter, hiding in plain sight for the entire history of astronomy. Their collective gravity would have been the hidden scaffolding upon which the first galaxies were built, gathering clouds of hydrogen gas around their invisible centers to form the brilliant islands of stars we see today. This vision transforms our understanding of the cosmic dark. The mystery substance that shapes the universe may not be a cloud of unknown particles, but a population of the most extreme objects in existence, a ghostly population of ancient black holes that has been weaving the tapestry of reality since the very beginning. These ancient black holes might be laying the groundwork for a cosmos that is not just expanding, but fundamentally changing state. A speculative but compelling theory suggests the universe is undergoing a vast and slow phase transition, crystallizing like water freezing into ice. In its hot, early youth, the cosmos was a seething, symmetric plasma where the fundamental forces were unified. As it expanded and cooled, it crossed critical temperature thresholds, causing the forces to differentiate in a series of cosmic phase changes, much the way liquid water suddenly reorganizes into the rigid, structured lattice of ice. The universe we see today, with its distinct electromagnetic, weak, and strong nuclear forces, could be the result of this ongoing process. We may be living inside a cosmic crystal that is still growing. What would this mean for the ultimate fate of everything? If the universe is still transitioning, it could eventually reach a point where the current vacuum of space is not the true, lowest energy state. A single quantum event anywhere in the cosmos could trigger a bubble of the new, true vacuum to form. This bubble would then expand at the speed of light, its boundary rewriting the very laws of physics as it goes. Inside this expanding frontier, the constants we rely on, like the speed of light or the strength of gravity, could be completely different, making chemistry, atoms, and life as we know it instantly impossible. The crystal would have finished setting, and our familiar reality would be a fossilized inclusion within a new, alien order. This is not a destructive explosion, but a silent reconfiguration of reality itself. The chilling thought is that this process could have already happened countless times in the eternal inflation of the multiverse, with each bubble universe representing a different crystalline phase. Our entire existence may be a temporary pattern in a cosmos that is gradually, inexorably, locking into its final, stable form. This strange idea of a cosmic crystal finds a bizarre echo in one of the most peculiar discoveries of modern physics, the time crystal. Unlike any other form of matter, a time crystal breaks a fundamental symmetry of the universe, not of space but of time itself. Think of a perfectly symmetrical, flawless diamond. It looks the same no matter how you rotate it in space. It has spatial symmetry. Now imagine an object that, in its lowest energy state, its ground state, does not look the same at all times. It undergoes a regular, repeating change in its structure, ticking like a clock, even when it should be perfectly still and cold. This is a time crystal, a structure that exhibits periodic motion forever without consuming any energy. It is the closest thing to perpetual motion the laws of physics will ever allow, not because it creates energy from nothing, but because it uses a clever quantum loophole to remain in motion eternally. The discovery sent shockwaves through the physics community because it fundamentally rewrites our understanding of equilibrium. A pendulum at rest is in equilibrium. A time crystal is also in a kind of equilibrium, but a dynamic one, forever oscillating between states. This is made possible by a phenomenon known as many-body localization, where quantum interference prevents the system from settling into a boring, featureless state, forcing it to remember its rhythm indefinitely. The cosmological implications are staggering. Could the universe itself be a kind of time crystal on the grandest scale? The cyclic models of cosmology, like Penrose's conformal cyclic cosmology, describe a universe that goes through endless cycles of birth, death, and rebirth. This is not a perfect analogy, but it points to a profound possibility. The fundamental fabric of space-time might possess a built-in perpetual rhythm, a cosmic heartbeat that drives these vast cycles. The regular ticking of a time crystal on a lab bench could be a microscopic model of the universe's own deepest, most enduring pattern. If true, then the hidden order we have been searching for is not just a static set of equations, but a dynamic, eternal pulse, a clockwork cosmos whose ticking is written into the quantum code of reality itself. The very fabric of space may be woven from threads of quantum connection. Two particles can be entangled, their fates linked across any distance in what Einstein called spooky action. Separately, Einstein and Nathan Rosen described bridges in spacetime, now known as wormholes, linking two distant points through a shortcut. For decades, these were considered two entirely separate, bizarre consequences of physics. But a revolutionary idea fuses them into a single, profound truth. The ER equals EPR conjecture proposes that entangled particles are not communicating faster than light. They are actually connected by a microscopic wormhole. Every spooky connection is a tiny, geometric bridge in the fabric of reality. This is not just a poetic metaphor, it is a potential geometric foundation for quantum mechanics itself. Imagine two coins, one here on Earth and the other on a planet in a distant galaxy. In our world, they seem separate, but if they are entangled, flipping one instantly determines the state of the other. The ER equals EPR conjecture suggests that secretly, invisibly to us, those two coins are connected by an unimaginably small wormhole, a Planck-scale tunnel that makes them, in a geometric sense, neighbors. This provides a stunningly elegant solution to the black hole information paradox. If you have two entangled black holes, the conjecture suggests they are connected by a giant space-time bridge, a wormhole. Information that falls into one black hole could, in principle, travel through this wormhole and exit the other, never being truly lost. The paradox vanishes because the information is not trapped inside a single black hole. It is preserved in the geometric connection between them. This implies something even more fundamental about our reality. What we perceive as empty, smooth space may not be the foundation of the universe. Instead, spacetime itself could emerge from a vast, cosmic web of quantum entanglement. The threads of spooky connection are not just embedded within space, they are the very stitches that sew space together. The solid ground beneath our feet and the vast emptiness between stars might be a collective illusion, a pattern that arises from countless trillions of these quantum threads. The universe is not a container for mysterious connections, it is the connection itself. This same principle of a self-regulating system might not be confined to our small planet. The Gaia hypothesis, proposed by James Lovelock and Lynn Margulies, suggests that Earth itself behaves like a living organism, where the biosphere, atmosphere, and oceans interact in a complex dance to maintain conditions suitable for life. What if this idea extends to the grandest stage imaginable? Could the entire universe be considered a living, self-organizing system? In this cosmic scale vision, galaxies are not just islands of stars but functional units akin to cells in a vast cosmic body. They form, evolve, and communicate through gravitational forces and energy flows, contributing to a larger, stable whole. Supermassive black holes at their centers could act as regulatory hearts, pumping energy and influencing the growth of galactic structures. The cosmic web, that immense lattice of dark matter and galaxies, would be the universe's circulatory system, with filaments channeling flows of gas and energy across billions of light years. Even the relentless pull of gravity and the push of dark energy could be seen as part of a cosmic feedback loop, a way for the system to regulate its own expansion and density, maintaining a delicate balance over eons. This is not to suggest the universe is consciously aware, but that it exhibits the emergent properties of a complex, adaptive system, one that naturally tends toward order and self-preservation. The laws of physics themselves could be the equivalent of its metabolic code, a set of rules that guide its development and response to internal changes. Is the cosmos a cold, mechanical clockwork, or is it something more organic, a single, breathing entity of unimaginable scale, in which we are but a fleeting, conscious moment? This perspective, where reality emerges from a web of connections, points toward a cosmos that is fundamentally structural. Max Tegmark's mathematical universe hypothesis takes this idea to its ultimate conclusion. It proposes that our physical reality is not merely described by mathematics, it is mathematics. We are not just discovering equations that approximate the behavior of the cosmos, we are living inside one vast, self-consistent mathematical structure. The particles, forces, and even the space-time they inhabit are not made of some mysterious physical substance, but are manifestations of abstract mathematical relationships and patterns. The universe does not compute mathematics, it is a mathematical object, in the same way that a triangle is a geometric object defined entirely by its own rules. This leads to a breathtaking and perhaps dizzying implication. If the universe is a mathematical structure, then every other self-consistent mathematical structure must also exist in just as real a sense. Every possible variation of the laws of physics, every conceivable geometry for space-time, every bizarre and counterintuitive cosmos that can be defined by a set of axioms is real somewhere in the multiverse. This is not the bubble multiverse of eternal inflation, but a far more vast and abstract landscape, the multiverse of all mathematical possibilities. In one mathematical structure, gravity might be 1,000 times stronger, making planets the size of marbles. In another, time might have 2 dimensions, creating a reality of unimaginable complexity. There would be a structure where the number pi is exactly 3, and the perfect circles of that universe would be foreign to our own. Our particular universe feels so real and concrete to us simply because we are a self-aware pattern within its specific mathematical framework. Our consciousness is the part of the structure that has become aware of itself. This idea dissolves the age-old question of why mathematics is so unreasonably effective at describing the physical world. It is not effective, it is fundamental. The reason the planets orbit in ellipses is not because of a force we call gravity, but because they are components in a geometric equation whose solution is an ellipse. The shock we feel when a quantum particle is in two places at once is just our limited perspective bumping against the broader logic of the probability wave equation we are part of. So where does this leave us? Are we nothing more than complex patterns in a cosmic calculation, living out our lives in a reality that is, at its heart, pure abstraction? The mathematical universe hypothesis suggests that the search for the hidden patterns of the cosmos is not a search for something embedded within reality, but a search for reality's own identity. The universe is not written in the language of mathematics. The universe is that language speaking itself into existence. Yet this cosmic language may ultimately spell its own violent end. Phantom energy is a hypothetical and terrifying form of dark energy, one that does not merely push the universe apart, but actively strengthens as it does so. In our current understanding, dark energy appears to have a constant density, meaning that as space expands, the amount of repulsive energy in any given volume stays the same. But phantom energy is different. Its density would actually increase over time. Imagine a car that accelerates not just by pressing the gas pedal, but by the pedal sinking deeper into the floor all on its own. The repulsive force of phantom energy would grow without bound, making the expansion of the universe not just constant, but exponentially self-reinforcing. This runaway acceleration would lead to a cosmic doomsday scenario known as the Big Rip. The timeline of this final annihilation is as methodical as it is horrifying. First, the phantom energy's grip would overcome the gravitational glue holding galaxy clusters together. The great cosmic cities of the universe would be wrenched apart, their constituent galaxies flung into the ever-widening void. Next, the expansion force would grow strong enough to tear apart individual galaxies. The Milky Way would be shredded, its stars scattered into the deepening darkness. Then it would be the turn of our solar system. The sun's gravitational hold on Earth would be broken, and our planet would be cast adrift. As the phantom energy continues to intensify, its power would reach into the very fabric of matter. With about an hour left, the force pulling on Earth would exceed the planet's own gravitational binding energy, and our world would be explosively torn asunder. In the final, fleeting moments, the expansion would overcome the forces that hold atoms together. Electrons would be ripped from their nuclei, and the nuclei themselves would be shredded into quarks and gluons. The universe would not end in fire or ice, but in a final, silent, and absolute dissolution. Every structure, every particle, every last bit of information that defined our cosmos would be pulled infinitely far from everything else, leaving behind not even a vacuum, but a perfectly featureless and desolate nothingness. This is the ultimate fate phantom energy promises, a universe that does not fade away, but is systematically and utterly unmade by its own most fundamental force. But what if even space-time itself is not a fundamental stage, but a collective illusion, an emergent property of something deeper and more basic? We are all familiar with temperature. When you touch a hot stove, you feel a distinct sensation of heat, but what is temperature really? It is not a fundamental substance. It emerges from the frantic, invisible jostling of trillions of atoms. A single atom does not have a temperature, it only has motion. Temperature is the collective behavior, the statistical average of all that microscopic chaos. Emergent spacetime theory proposes that the fabric of the cosmos works in a remarkably similar way. The three dimensions of space and the one dimension of time that we experience may not be the bedrock of reality. Instead, they could be a large-scale consequence, an average that arises from the interactions of countless fundamental quantum building blocks. We do not yet know what these fundamental components are. They might be tiny loops of string, pixels of information, or something even more abstract. But their interactions, their quantum entanglements and correlations, could be what weaves together the smooth, continuous spacetime we perceive. This idea is not just philosophical speculation, it is a leading path toward solving the greatest problem in theoretical physics, the quest for a theory of quantum gravity. Our two most successful theories, general relativity and quantum mechanics, are fundamentally incompatible. General relativity describes gravity as the elegant curvature of a smooth spacetime continuum, while quantum mechanics describes a fuzzy, probabilistic world at the smallest scales. The equations of general relativity break down completely in the extreme conditions of the Big Bang or inside a black hole, where quantum effects must dominate gravity. The problem is that we are trying to quantize gravity within a pre-existing spacetime arena. But if spacetime itself is not fundamental, the conflict dissolves. In the emergent spacetime view, gravity is not a force that propagates through space. Gravity is the thermodynamics of spacetime. Just as heat emerges from atomic motion, the force of gravity could emerge from the underlying dynamics of these spacetime atoms. This means that Einstein's beautiful theory of general relativity would not be wrong, but it would be an approximation, a very good description of the emergent, large-scale reality. Much like the laws of thermodynamics perfectly describe the behavior of gases without needing to track every single atom. This radical shift in perspective completely transforms our understanding of the universe's origin. The Big Bang would no longer be viewed as the moment when space and time suddenly sprang into existence from a singularity. If spacetime is emergent, then the Big Bang marks the point where the underlying quantum components became so highly entangled and correlated that the properties of space and time as we know them crystallized into being. There was no before because time itself did not exist in a recognizable form. The universe was a boiling quantum soup, and the Big Bang was the phase transition when spacetime froze out, much like ice crystals forming in water. This suggests the cosmos could have a deeper, non-spatiotemporal beginning, a state of pure quantum potential from which everything we know, including the dimensions we move through, was born. If a black hole is a cosmic drain from which nothing can escape, what would its opposite look like? A white hole is exactly that, a hypothetical region of spacetime where nothing can enter, only exit. It is a fountain of pure, relentless output, a place where matter and energy are violently expelled into the universe. Mathematically, a white hole is a perfectly valid, time-reversed solution to the equations of general relativity that describe a black hole. If you were to take the film of an object falling into a black hole and run it backwards, you would see an object being violently ejected from a white hole. This is more than just a mathematical curiosity. It forces us to confront the true nature of gravity and time. The event horizon of a white hole is a one-way street in the opposite direction, a boundary you can cross outward but never cross back into. While we have overwhelming evidence for the existence of black holes, a confirmed white hole has never been observed. Their very nature makes them difficult to detect, as they would only reveal themselves in a brilliant, sudden eruption of energy and particles, a flash in the cosmic dark that would vanish as quickly as it appeared. So where could such a bizarre object be hiding, and what purpose could it serve in the grand architecture of the cosmos? One compelling idea is that a white hole could be the other end of a black hole, connected by an Einstein-Rosen bridge or wormhole. In this vision, the matter and energy swallowed by a black hole in one part of the universe is not lost forever, but is instead transported through the wormhole and spewed out of a white hole in another location, or even in another universe entirely. This offers an elegant solution to the information paradox, preserving the cosmic ledger by ensuring everything that falls in eventually comes out somewhere else. An even more radical proposal suggests that the Big Bang itself was a primordial white hole event. Instead of a singularity of infinite density, our entire cosmos could have begun as the explosive output of a white hole in a larger, pre-existing meta-universe. Our universe is not the starting point of everything, but the result of a cosmic eruption from another reality. This would mean the Big Bang was not the beginning of time, but a transition, a bridge from one state of existence to another. The universe would be born not from nothing, but from something, a torrent of matter and energy erupting from a white hole singularity. This idea beautifully mirrors the cyclic and interconnected models of cosmology, suggesting that our reality is just one link in an endless chain of cosmic respiration, forever balanced between the inhale of the black hole and the exhale of the white hole. This relentless selection of stable states might be the very mechanism that carves our solid reality from the quantum fog. Quantum Darwinism offers a fascinating answer to one of the most persistent puzzles in all of physics. How does the weird, probabilistic world of quantum possibilities transform into the single, definite world we all seem to share? The theory suggests that reality becomes objective through a process strikingly similar to natural selection. In the quantum realm, a particle exists in a blur of potential states, a superposition where it is, in a sense, everywhere at once. But when this particle interacts with its environment, something crucial happens. The information about its state is not just measured by a scientist in a lab, it is constantly measured or copied by the countless photons, air molecules, and dust particles constantly bumping into it. Think of a single, special coin spinning in a vast, dark room. You cannot see the coin itself, but imagine that every time a tiny speck of dust touches it, that speck takes a perfect imprint of whether the coin is showing heads or tails at that exact moment. Soon, the air is filled with thousands of these dust specks, each carrying a copy of the same information. Now, anyone entering the room does not need to see the original coin. They can simply look at any of the dust specks and know the coin's state. The information has become public, objective. Quantum Darwinism proposes that this is exactly how our classical world emerges. The environment acts as a witness, constantly making copies of the most stable, robust quantum states. These are the states that can survive this process of being constantly observed without collapsing into chaos. Other, more fragile superpositions are simply wiped out, unable to leave a lasting imprint on their surroundings. So, the reason we all agree that a table is solid and in one specific location is not because its fundamental particles are inherently solid or located in one place. It is because the stable state of those particles has been massively replicated into the environment around it. The table is continuously broadcasting its position and solidity through a billion tiny interactions with the air and light, and our senses are simply tapping into that publicly available information. This process, called environmental decoherence, explains why we never see tables in superposition, existing in two places at once. Those states are too delicate, they are erased by the slightest interaction, while the stable, classical state is amplified and spread everywhere. Our shared reality, then, is not the only possible one. It is simply the one that was fittest to survive, the quantum possibility that was best at getting itself copied. We perceive the universe not in its raw quantum glory, but through the consensus report generated by trillions of environmental witnesses. So when you look at your hand, you are not seeing its fundamental quantum nature. You are seeing the version of it that has won the evolutionary struggle to be replicated, the objective reality that has been bred into existence. This invisible halo is the true master of the galaxy. We see the glittering spiral arms of stars and gas, but they are merely tracing the outline of something far more massive and completely unseen. Every galaxy, including our own Milky Way, is embedded within a vast spherical cloud of dark matter, a gravitational anchor that holds the entire structure together. Without this hidden scaffolding, galaxies would simply fly apart. The stars on the outer edges of a spiral galaxy rotate at speeds that defy the pull of the visible matter alone. According to the laws of gravity, these distant stars should be moving much more slowly, like planets in the outer solar system. Their surprising velocity is the primary evidence that they are caught in the irresistible grip of an immense invisible mass, a dark matter halo that extends far beyond the galaxy's luminous edge. This hidden pattern dictates not just the speed of stars, but the very birth of the galaxy itself. In the early universe, slight ripples in the density of dark matter provided the initial gravitational seeds. Ordinary matter, the stuff that makes up stars and planets, was then drawn into these dark matter wells, pooling and condensing until the first stars ignited. The visible universe was literally painted onto an invisible canvas of dark matter. So what is this mysterious substance that comprises over 80% of all matter in the cosmos? The leading candidate for decades has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. As the name suggests, it would be heavy by particle standards and interact with normal matter only through gravity and the weak nuclear force, making it incredibly difficult to detect. Dozens of sophisticated experiments are buried deep underground, in mines and tunnels shielded from cosmic rays, all waiting for the once-in-a-lifetime ping of a WIMP colliding with an atom in their detector. Yet, so far, the silence is deafening. This lack of discovery has fueled the rise of another compelling candidate, the Action. Billions of times lighter than a WIMP, the Action was originally proposed to solve a different deep puzzle in particle physics. It would be a ghostly particle flooding the universe and could potentially be detected by converting into a photon in the presence of a powerful magnetic field. Experiments are now actively hunting for these elusive phantoms. Could the dark matter halo be a cloud of WIMP, a sea of actions, or something even more bizarre that we have not yet conceived? The answer remains hidden, written in the silent, rotating patterns of every galaxy, a cosmic secret held tight by the dark. This ghostly halo of dark matter is not the only cosmic phantom. There is another, even more elusive particle streaming through your body in countless trillions every second, a ghost from the heart of the sun and distant supernova. The neutrino is so ethereal it was long considered a mere speck of nothing, a particle with no charge and, most importantly, no mass. For decades, this was a foundational truth in physics. Then, deep underground, in a mine filled with ultra-pure water, a strange discrepancy emerged. Scientists were counting neutrinos arriving from the sun, and the numbers did not add up. They were detecting only about a third of the neutrinos their models predicted. The rest had seemingly vanished into thin air. The solution to this solar neutrino problem was not that the neutrinos were disappearing, but that they were changing. They were caught in the act of a breathtaking transformation called neutrino oscillation. A neutrino born in the sun as one type, the electron neutrino, could, on its long journey to Earth, spontaneously change into a muon or tau neutrino, types that the original detectors were blind to. This was a discovery of profound significance because for this oscillation to be possible, neutrinos must have mass. A massless particle, like a photon, travels at the speed of light, and from its perspective, time does not pass. It cannot change or evolve, but a particle with mass, even an infinitesimally small one, moves just a fraction slower than light, allowing time from its own reference frame to tick forward. This internal clock is what allows the neutrino to oscillate, to shift its identity as it flies through the universe. The mass is tiny, a fraction of the mass of an electron, but its existence shatters the standard model of particle physics, our most complete catalog of the subatomic world. The model had no place for massive neutrinos. Their weight, however slight, forces a rewrite of the fundamental rules. This tiny, hidden property of the universe's most ghostly particle has massive implications for the cosmos. It may even hold the key to one of the greatest mysteries of all, why we exist. According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate in a flash of pure energy. If the universe began with perfect symmetry, all of it should have annihilated, leaving behind a sea of radiation and nothing more. Yet here we are in a universe made almost entirely of matter. Something must have tipped the scales, a process called baryogenesis that favored the survival of matter over antimatter. The oscillation of neutrinos could be a crucial part of that process. A related phenomenon known as CP violation describes a slight asymmetry in how particles and antiparticles behave. If neutrino oscillations also violate CP symmetry, it could mean that neutrinos and antineutrinos oscillate at slightly different rates. Over the first crucial moments of the universe, this tiny bias could have been amplified, leading to the overwhelming dominance of matter we see today. In this scenario, the very substance of our world, the atoms that form our bodies and our planet, may be a direct consequence of the secret, shifting nature of these cosmic phantoms. The answer to why there is something rather than nothing may be written in the silent, oscillating dance of the neutrino. This ancient sea of ghosts flows through the cosmos as a cosmic neutrino background, a relic from the universe's very first second. While the cosmic microwave background shows us the universe at 380,000 years old, this neutrino sea is a far older fossil, a snapshot from when the cosmos was barely a second old. These neutrinos were untethered from the primordial plasma even before light could travel freely, making them the very first messengers to escape the universe's hot, dense infancy. They are everywhere, a low-energy whisper from the dawn of time, with trillions passing through your body every single second. Yet they are so elusive that detecting them directly remains one of the greatest challenges in modern science. These relic neutrinos hold a unique key to understanding the universe's earliest moments, a period forever hidden from the view of light. Their properties, if we could ever measure them, would reveal the exact conditions during that first second of creation, telling us about the violent processes that forged the first atomic nuclei, and perhaps even shedding light on the mystery of why matter came to dominate antimatter. The quest to capture these cosmic ghosts is a technological marathon requiring detectors of unimaginable sensitivity, chilled to near absolute zero and shielded from every other form of interference. To catch a whisper from the first second of everything, we must first learn to hear the universe in perfect silence. The silent whisper of the neutrino background is a call from the beginning, a reminder that every hidden pattern we have uncovered points toward a deeper, unified truth. For over a century, physics has been split between two magnificent but incompatible descriptions of reality. General relativity paints a masterpiece of cosmic gravity, where planets and galaxies dance on the curved fabric of spacetime. Quantum mechanics reveals a frantic, probabilistic underworld where particles pop in and out of existence and defy location. One is the law of the very large, the other the rule of the very small, and where they meet at the singularity of a black hole or the first moment of the Big Bang, our mathematics breaks down into nonsense. The greatest quest in modern science is to find a single, elegant framework that can weave these two worlds together, a final theory of everything. This would be the ultimate hidden pattern, the fundamental equation from which all of reality, from the spin of an electron to the expansion of the cosmos, could be derived. The two most prominent candidates offer radically different visions of this unity. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. An electron is not a dot, but a string vibrating at one specific frequency. A quark is the same kind of string, just vibrating at a different note. In this symphony of the very small, gravity and all other forces emerge naturally from the harmonies of these strings. The theory, however, demands a shocking price for this unity. For the mathematics to work, these strings must vibrate in not just the 3 spatial dimensions we experience, but in 10 or more dimensions. The extra dimensions, the theory suggests, are curled up into a space so infinitesimally small that they are completely hidden from our perception. The entire universe we see may be a 3-dimensional slice of a far richer, higher-dimensional reality. Its main rival, loop quantum gravity, takes the opposite approach. It does not add new dimensions, but suggests that space-time itself is not smooth and continuous. Instead, it is woven from a fabric of tiny, finite loops, a network of a billion intersecting threads. Think of the fabric of your shirt. Up close, it is not a smooth sheet, but a grid of woven threads. In the same way, space may have a fundamental, granular structure at the smallest possible scale, the Planck length. In this view, gravity is not a force transmitted through space, but a natural consequence of the changing connections within this woven network. Time itself may be an emergent property, ticking forward as the network of loops reorganizes itself. One theory adds hidden dimensions, the other quantizes the very stage upon which reality plays out. Both are monumental intellectual achievements, yet both remain unproven, their predictions currently beyond the reach of our most powerful particle colliders and telescopes. This leads to a profound philosophical dilemma. Would a successful theory of everything represent the end of physics, the final revelation of the cosmos's master blueprint, leaving no more fundamental mysteries to solve? Or is the universe fundamentally inexhaustible? Perhaps any final theory would simply push the ultimate question of why this particular set of equations exists one step further back into the realm of pure metaphysics. The search for the final pattern may be an infinite journey where each answer unlocks a deeper, more beautiful question, forever reminding us that the greatest secret of the cosmos might be its endless capacity for wonder. From the spiraling galaxies of the Fibonacci sequence to the ghostly whisper of the cosmic neutrino background, our journey has spanned the full breadth of cosmic mystery. We have ventured into a holographic projection, questioned our reality within a simulation, and stood at the edge of an eternal, cyclic cosmos. We have seen how quantum threads may weave the fabric of space itself, and how our own observations might freeze reality into being. Each theory, from the unsettling Boltzmann brain to the elegant dance of ER equals EPR, represents a different facet of the same relentless human endeavor to find the hidden order in the chaos. This quest for patterns is the very engine of science, a process of perpetual wonder that thrives not on final answers but on ever deeper questions. The universe is the ultimate puzzle, an ancient, encrypted text written in the languages of mathematics, light, and gravity. And every single one of us is a detective, equipped with curiosity and reason, tasked with deciphering its clues. So we turn the investigation over to you. Which of these 30 theories reshaped your view of reality? Share your most compelling cosmic clue in the comments below, and subscribe to join us on the next deep dive into the universe's greatest mystery.